Welcome to Happy Maths Hour. This is the second part 2 of To Bet or Not to Bet. Toni.
Well, that's the question. And we're going to talk about gambling today. Now, interestingly, the modern study of probability, which is so important in so many ways in applying mathematics, of course it is, to insurance and many other things. And we've been considering it in relation to the pandemic. It all started with gambling. Of course, gambling has been going on for thousands of years in many cultures around the world. But in the 16th, 17th century and since then, prominent, really top-ranking mathematicians have turned their attention, and they were probably gamblers too, I would say. They've turned their attention to the theory behind gambling odds, and then they've formalized that in some rather abstract mathematics. It comes to it at times in the theory of probability. So it originated.
Do you think they were looking for an edge?
Well, maybe they wanted to break the bank of, one of these gaming houses. So Cardano was the first one and to analyze games of chance in this way. And then Fermat and Pascal. Huggins wrote a book about it. And then finally, Laplace in the 19th century, he completed what's now known to be the complete basic theory. I mean, he formulated probability as we know and love it, study it today. So what we're going to talk about today is national lotteries. Well, we're going to take our own Mathsland lottery, and here the balls are numbered 1 to 49, and to win the jackpot, you need to choose or have on your ticket the 6 winning balls from that draw.
So 6 out of 49.
Yes, that's it. And there are smaller prizes, but that's the jackpot that everybody wants to win. Now, we've talked about last time about much smaller lotteries with fewer balls, but now we're going to go to the 49 balls, similar to many national lotteries were 49 balls. Some are now a few more, 52, 59. And so let's think about 49. The probability of all my 6 numbers winning the jackpot is 1 in 14 million. We're going to discuss that. So
okay,
if
I'd like to just pause for a moment and think what that means. So 14 million. The population of the UK is about 80 million. So it's like,
well, you've got to be 18 to gamble, and not everybody buys a ticket. So I'm not sure that's the best way to look at it. I think the best way is that if somebody who wanted to win bought 10 tickets a week, right? When you calculate what this 1 in 14 million means, it would be thousands of years on average before I'd win a prize if I did that. And of course, I might be super lucky and win this week. That's the nature of probability. But on average, it would be thousands of years. So it's just like life insurance. If you take out a life insurance, Caroline, you might live till you're 110, and then it'll cost the insurance company a lot of money. Not likely, but it could happen. Okay, or you could die tomorrow, heaven forbid. Okay, and then they would be paying out a great deal of money, and you would have hardly paid any premiums at all. So what insurance companies do is to work out, on average, across hundreds of policies, what is likely to happen, and they make sure they're going to make a profit. Okay, so it's the same way with gaming houses and the national lottery. So it'll be thousands of years on average. Well, is it worth it? But one of the things about the national lotteries is that, of course, they do give money to charity. And that gives people some sort of sense of, they're doing good to be buying a lottery ticket.
Well, that's my view on it. If I buy, which I've never done, a lottery ticket, it would be to make a donation to the lottery fund, which does good works.
That's a good philosophy, because you're not likely to win. Now, all possible outcomes for 3 numbers chosen from 6. Let's just remind ourselves, let's look at it if you didn't see it last week. So we've listed all possible triples of numbers, and there's all of the numbers with the number 1 and 2 others, and there's the numbers now including 1, or now we're building up in the left hand one, the numbers with 1 and 2 others, in the middle 2 and 2 others, and then on the right then 3 and 3 others, and 3 and 2 others, and can you see that we've got them all there? Just look across the rows and you'll see that the blocks, you'll see we've got 1 with every other possible combination, and then as you go to the right there are no more 1s there, but then there's 2 with every combination we haven't already seen, and then there's 3 with the remaining triples that include 3, and then finally 4, 5, 6. So one of these triples of numbers must be the winning combination, and there's 20 of them, so there's a 1 in 20 chance of winning. Now, there are 2 ways to find the probability of winning the top prize. One is listing all the possible results as we've done here. And the other is using a tree diagram method, which we'll come to in a minute. But let's think of 49 numbers and listing 6 possibilities. I wouldn't like to have to list them all, would you, Caroline? All the possible...
No, I think not. I think this is where doing things on paper or using a computer comes into its own.
Well, even papered, if you were going to write it down, it would take you days. It would be a big job to just check you got them all and do it systematically. So I don't think you want to use this method for big numbers like 49, but we're going to look at another method which is powerful, and we'll see how that works. So here, again, reminding you what we're going to do, 6 balls chosen from 49. Now let's think about it. And a tree diagram is what we're going to use. Now, when we did that for 3 numbers, the tree diagram is shown you there, 3 numbers chosen from 6. And the probability of winning, the top prize, is 3 out of 6. So when you make your first, the first ball you choose, there's 6 winning balls, and this is the 3 out of 6. There's 3 winning balls out of 6, and so you've got a 3 in 6, or a half chance of of picking a winning ball. Then, now we want you to pick all 3 winning balls and see what the probability is. Now, the second one picked out, if you've already got 1 winning ball, there's only 2 left in the bag, and there's only 5 balls left in the bag. So the chance your second one is a winner is 2 out of 5, leaving only 1 winning ball in the bag and 4 altogether. So the chance that the third one is a winner is 1 in 4. So that works out at 1 in 20. So that's the
sequence. That's what the sequence you have to go through in order to win.
Yes, and that is calculating it using this tree diagram method. So on this branch of the tree, if you could see where my cursor is, that represents a choice of having a winning number or not with the first pick. And then
Toni, I'm just going to say it's in the think cloud. It's behind the words in the think cloud.
Yes, it's here. So you have to go up this branch, and then having won, you have to go up that branch, which is another winning number, and then up that branch, which is another winning number. So we discussed that last week, and how you work it out using the tree diagram with multiplying those 3 fractions together. And the problem for the 6 numbers in 49, game is solved in the same way. Okay, but now you've got to imagine a tree diagram like that, but extended a bit more, three more sets of branches. So we've thought about the 3 balls in 6 game. Now we're going to look at the 6 balls in 49 game. But now, this time the writing in the thought bubble says we have 6 numbers. The tree must be extended. We have 6 numbers chosen from 49. And the tree must be extended 3 more times. So can you imagine it going off to the right? I don't want to draw it because it's a complicated thing to draw. We've really got to be able to think mathematically.
So it's going to go, if we imagined it would go off to the right and have 6 columns. And then
it's going to have, it's got 4 endings, 8 endings as it starts, as you see it on the right. Now, from each of those endings, you're going to have a branch with going 2 ways. So there's going to be 16 more ends. And then it's going to be 32 and then 64 ends.
Right.
Now, only one of those sequences of drawing the balls is going to lead, the 6 balls now, is going to lead to a win. And it's the one that's on the top all the way. So of the 32...
The winning one is the high road.
It's the high road. That's a good way to put it. But we're not going to draw the tree diagram. We understand that it's the top, the high road that you'd use on the tree diagram to get there all the time, starting from the top branch each time. Then that will give you the way of calculating the fraction. And it's just an extension of what we were doing just now. So the probability that my first number wins is 6 out of 49. 6 winners.
So
6 winning.
This is following the high road.
Indeed. 6 winning balls out of 49 altogether. Now, if I've won, if that first ball is a winner, there will be then 5 winning numbers left out of 48. So the probability that both my first and second numbers win is 6 over 49 times 5 over 48. And so it goes on. So you see, when it was 3 balls in 6, I only had 3 fractions. Now I've got 6 fractions. And it's a very similar pattern to the way we write that down and calculate it. It's 6 out of 49 multiplied by 5 out of 48, multiplied by 4 out of 47, multiplied by 3 out of 46, multiplied by 2 out of 45, multiplied by 1 out of 44. And each time the top of that fraction has got the number of winning balls left in the wheel or whatever, and the bottom of the fraction has got the total number of balls altogether in each fraction at each stage. And when you multiply that out, it's 7.15 times 10 to the minus 8. It's quite a small number. Okay, it's quite a small number. And so what that means, it's 1 in 14 million. So, I mean, if it's, so that's what you do. You have to divide it into 1 to get how many chances. I mean, how many times you'd have to sort of have a go, buy a ticket if you were going to win. 1 in 14 million. Okay, so there it is repeated again and enlarged just to emphasize it. Think about it. Think about going along the high road, as Caroline called it, on the probability diagram, tree diagram. Now, if you bought a ticket once a week, then you would expect to win once in about 270,000 years. You see,
No, wait, what? I knew it was bad.
yes.
So
Well,
if
the
I
thing
bought
is,
a ticket, I need to replay that. Hold on, wait, hold your horses. So people that buy a ticket once a week, thinking they might win once in their lifetime, perhaps
they might be lucky.
Wouldn't that be nice?
They might be lucky. Mm-hmm.
Well, they might be lucky, but they could 270,000 years.
Yes,
That's not. I mean, no.
You see, all you do is, the 50 weeks in a year. Every time you buy a ticket, you've got a 1 in 14 million chance of winning, right? So how many years would it take? Well, just divide that by 50.
Well, it's not about doing the calculation, Toni. It's about just look at that number. 270 is like 4 times the average. Just 270 is 4 times the average life expectancy times 1,000.
But some people get lucky. Yeah, I know. Well, that's what I'm saying. Some people get lucky, though, don't they?
I think I'll stick with my luck of not buying lottery tickets.
Ah, you've got other things you can spend your money on, haven't you? I have too.
I certainly do.
So
I can just give it straight to AIMSEC that we're doing these videos for.
Oh, thank you. The UK lottery has 59 balls and the South Africa lottery has 52. I think the Euro Millions has got 49. So if you've got more balls and only six numbers still, but more balls to choose from, there's an even smaller chance of winning.
Right. Now, okay. Well, I'm glad I didn't know the numbers, but now that I do know the numbers, I knew they were bad, but I didn't know they were that bad.
So there are smaller prizes, actually. They're not big prizes, but if you get 5 balls or 4 balls, you can win a smaller prize, and it's quite a it's quite a nice amount of money to have. But the jackpot, no, that doesn't come up your way unless you are very, very lucky. So that's the big question. Are there better ways of spending your money? And yes, almost certainly there are. However, for some people, it's really a well, I think it's important to say that for some people, gambling is something that they enjoy. They go to watch the horses, they enjoy watching the races, or they go and watch a cricket match or a football match, and they have a little gamble, they have a little bet.
They call it a flutter in racing. They call it a flutter. I'll have a flutter. I guess that just means gives you the butterflies. You've got that little extra sense of excitement.
Yes,
and I've got friends who go to Las Vegas and they set themselves a budget. They're clear. They're going to Las Vegas. They're going to spend a certain amount of money on the fun that they have gambling.
Yes, well, I can understand in a way, but it wouldn't be my way of spending my time. I mean, in South Africa, they've got this big Sun City, and it's right next to a big safari park, which is absolutely beautiful. And I've been to the safari park, but wild horses wouldn't have dragged me into the casino. For some people, it's a way of spending their time. Other people watch television, other people have different hobbies, and it can be harmless, but it sometimes is not. And what starts off in a small way gets bigger and bigger, and it becomes an addiction, and then it is it's a serious problem. It is
many times it's not. It's really it can be horrendous, and too many families are affected by gambling problems.
Yes, that's true. But some things like bingo, for instance, where people pay to play, and it's an important part of their social life. They go out and they meet other people, and maybe they live alone, and as they fill in the numbers on their bingo card.
The statistics aren't quite the same with bingo. I mean, you're paying, like in England, you pay maybe £5 or £10 to go for one evening playing bingo. You're socializing with everyone around the table, and you might get a bingo on your card. And
which wouldn't be a big prize, but you go home with more money than you came with, as it were, probably.
That's not really, it's not gambling that's going to cause problems. It's just an evening's entertainment.
But you see, that's interesting as you say that. But then there is the halls where you play the machines, and online, and those
you've got the what we call the one-arm bandits. That's different. That's not the same thing. That people just feed those. They just feed and feed and feed, and it gives them a little bit, so they put it back and a bit more and a bit more. But also the online gambling is they've got it down to a fine art. They've got it down to a science of how to tempt people in with free gambling. Basically, they get money, and they get money for nothing because it's free. And then so they put some money back in, and it really is down to science and psychology, and they've got it all worked out to lure people in and trap them.
Yes. I mean, I think. Oh, do you remember beetle drives, Caroline? I don't know that there are beetle drives these days, but they used to be quite popular. Do you remember? Oh no! Well, you drew a beetle, and you had to have 6 to get the body, 5 to get the head, and other numbers to get the antennae and the legs, and the first person to get a beetle, to be able to draw a beetle, shouted out "beetle."
Okay, no, I haven't had that experience.
Okay, well they were just another way, and I don't think
that sounds like fun though.
I don't think much money changed hands with beetle drives. And okay, so sometimes people play card games that are games of skill, are really quite hard to play, but put some money on it. They play games like bridge or even chess sometimes. I don't think it's so they gamble on chess so often, but they do gamble on bridge.
I think the audiences gamble on chess. It's one of those things that gambling happens about, not necessarily the people that are doing the players.
I think that's true. Yes, that's true. Okay, so let's move on to consider this problem, and it's quite a puzzling problem, and yet it's a very simple problem to state, to see what's going on. This is Monty Hall was a quiz. It was a quiz master. This was a quiz show, and the big attraction was this opportunity to win a car. So there were 3 compartments. One of them had a super new sports car behind the door, and the other 2 had goats. So you go along, if you're a contestant and you want to win a car, so you choose one of the doors, and you have a 1 in 3 chance of winning a car and a 2 in 3 chance of winning a goat. Or
if you win a goat, do you have to clean up after it?
Maybe the goats make a paper cutout. I don't know, but anyway, I think it might have been a real goat. Okay, now, so supposing you choose door 1, Caroline. Now, of course.
Okay, so I've chosen door 1.
And the host or quizmaster knows exactly where the car is. Okay,
that's you.
All right, so I know where the car is. So I open one of the doors to show you a goat, and now you know that compartment doesn't have a car behind it. So you know that.
So now I know that my door might have a car, because for sure, well, I can see one door that has a goat, which still leaves one door with a car. So now I've
Yes.
got 1 out of 2 chance to find the car, right?
Well, that's what a lot of people think, which is interesting. That it doesn't matter which door you open now, because you've got a 50-50 chance of winning the car. You know it's in one of those two places. It's behind door 1 or door 2. Now,
Yeah, so
people
it's just eeny, meeny,
argue.
miny, mo.
Well, you're in good company, Caroline, because many people argue that, but it's not right. Now, why isn't it right? The question is, should you change? And we'll look at this in different ways.
Now, wait, does this depend if you know which door the car is behind?
Oh, yes. I mean, the whole thing would have been ruined if I was Monty Hall and I opened the door and there was the car, you know.
Well, that's true. So logically, you have to know at least which
Indeed.
door the car isn't behind, which tells you which door the car is behind.
Yes,
okay, so
indeed.
you know
Yes.
which door
Yes,
hides
I
the
do.
car. So I could have been
And,
lucky. First time around, I could have won the car.
but there was a 1 in 3 chance. Now remember that, because
That's
that
not bad.
chance. No,
I'm quite upset that I didn't win the car now, because 1 in 3 chance, a pretty good odds against 14
wait a minute.
million.
You could. Yeah, well, that's something else. This is you have quite a good chance of winning the car. Okay, so the point is that when you get some more information, when I open door number 3 and show you the goats there, your chance of winning that car was still 1 in 3, and it doesn't change. Now let's look at the possibilities. There's 3 diagrams. Now the bottom band there's 2 lines, okay, and they show you the 3 situations.
Okay.
On the left, you've got the bright light, yellow light showing a car at the bottom. And then above that, there's 2 situations where you have a goat behind the door you've chosen. So it's
So the
either
first 2 is
the goat.
No.
The
last one is that I happened to just choose the door that had the car.
Yes. But notice that was a 1 in 3 probability.
Right.
And the whichever of the other I know that there's a goat behind the other 2 doors, so it doesn't matter whether I open door number 2 or door number 3. But that's still only one third of the times that this show is run like this. 1/3 of the times, on average, that's what's going to happen. The contestant will have chosen the door which has the car behind it. Okay. But in 2/3 of the time, the contestant will have chosen the door which has got a goat behind it.
Yeah.
Now, in either case, the other door that isn't opened has got the car behind it, because the open door has shown a goat. That's no good. And the closed door has the car behind it. So if your door doesn't have a car behind it, in 2 out of 3 times, the closed door does. And so you should switch, because your chance.
I just realized something, Toni. I know we have spoken about this, but it's like, even if you at the beginning you've chosen the door with a car behind it, you don't know that.
Exactly.
Monty Hall knows it, but I don't know it.
So you see, Monty Hall can be really clever here, because he knows that 2 out of 3 times it's in your interest to choose. So he'll try to persuade you with smooth talk into changing. He'll try even
Clever
harder.
psychology, like a magician, suspension
Yeah.
of disbelief,
He-
forcing
he-
a choice.
He'll try even harder if you've chosen option 3 with the door with the car behind your door. He'll try even harder to convince you that more often than not it's a good idea to
change.
Yeah. So at the start, the probability that box 1 contains a car was 1/3, and that doesn't change. Given the extra information, we know the probability that the unopened box contains the car is 2/3. So you should change.
Wow.
Well, let's look at it. It isn't.
It's a big difference.
It's a good problem. Now let's look at it, the same problem in a slightly different way. Okay, the same thing happens, but now we're going to look at the same analysis, but in a different way. Okay, so now this shows you very clearly the 1/3, 2/3 ideas. So your door has a 1/3 chance. Sorry, the car has a 1/3 chance of being behind your door, the one the player picks.
Yep.
And a 2/3 chance of being behind one of the other 2 doors. So if you look
simple.
at the
3 doors.
panel on the left, okay. Now on the right, you see the host opens a door. The odds for the 2 doors, 2 sets don't change, but the odds move from 0 for the open door, and what they become is 0 for the open door and 2/3 for the other door. So if he opens door number 3, in 2/3 of the cases, the car is behind door number 2.
That is so counterintuitive.
Yeah, it is, isn't it? Now,
it's just messing with my head.
Well, you know, Caroline, what happened when this was a quiz show in America, and when it was broadcast and then discussed by a lot of people, including a lot of mathematicians, people argued and argued and argued by it. And many people said, oh, it was 50-50 anyway, so it didn't matter whether you changed your choice or not. And then this was the 1/3, 2/3 is the solution, so that you should change. Well, sometimes it works against you. Yeah, people find it very difficult to understand the argument. But so we've got this video. Would you like to show the video, Caroline?
Yes, indeed.
I can't hear
So we have
anything.
these 3 doors. One hides this shiny red sports car. The other 2 have these worthless goats. You, the contestant, choose a door. Let's choose door 1 in this example. The game show host, Monty Hall himself, who knows what's behind each door, is then forced to reveal a goat from behind one of the 2 remaining doors. You're then given a choice to stick or switch. With 2 doors remaining, it seems some of you think this has become a 50-50 choice. Stick or switch. It doesn't really matter. There are 2 doors. One's got the car and one doesn't. But that's not true. And your best chance of winning is to switch. Now, the reason for this is an important fact that I cannot emphasize enough. Monty Hall, the host, knows what's behind all the doors, and he's forced to show you a goat from behind one of those 2 remaining doors after your first choice. This is very important. There is information here that's about to be put into the system. Let me explain what happens. When you made that first choice, there was a 1 in 3 chance that the car was behind your door. Surely we agree here. Now, in that situation, Monty had 2 goats he could have revealed to you from behind these other 2 doors. That's not very helpful. And of course, if you then switched, like I tell you should, you'd have moved away from the car and lost. I'm sorry, I just lost you a sports car. I apologize. But let's be honest, there was only a 1 in 3 chance of that happening. Let's wipe the slate clean, or the brown paper clean. And now this time, let's imagine your first choice was that dreaded goat. Now this is twice as likely. There's a 2 in 3 chance that this is what you've done. Agree on that, right? 2 in 3 chance you've chosen a goat. So this scenario, of course, should be of more interest to us. It's the more likely scenario. And this time, you have forced Monty's hand. He knows where the one remaining goat is. He knows it. And he has to show it to you. In this case, in 2/3 of the games you ever play, he is indirectly telling you exactly where the car is. It's here, behind the door he didn't open. Let me say that again. In 2/3 of the games, Monty can only open one door because he knows, and therefore you should know, the car is behind the other one. And because you know this, you should switch. Now, you don't know for sure this has happened. There's a 1 in 3 chance this hasn't happened. But there's a 2 in 3 chance it has happened. It's more likely to have happened. It's more probable. So there you go. Switch, switch. Probability tells you to switch. And this is because of Monty's knowledge. If Monty didn't know what was behind the doors, this would be completely different. Then after his big reveal, you'd be none the wiser. And the odds would indeed be 50-50. You may as well stick. But it's also worth noting in that case, 1/3 of the time, Monty would accidentally open a door that reveals a car. That's not the game we're playing. Monty knows where everything is and won't reveal the car. That's the rules. Monty has the knowledge, and therefore you have the knowledge. And knowledge, as they say, is power. Leave a comment.
Okay, well, that's just what I said, but said in a different way with some amusing cartoons. Okay. And I got my pictures from the Wikipedia. So you can go to that link there to Wikipedia and read more about it if you want. Now, we had this problem, the lucky numbers problem, and we put a new problem every day on AIMSEC on the Facebook page. And last year sometime, we put this lucky numbers game up, and somebody called Matt Insel in University of Missouri in America posted a comment to say, what about Monty Hall for your game? And so now we're going to look at our lucky numbers, but a Monty Hall version of it. Now this is more difficult, more tricky than the usual Monty Hall with the goats, with only 3 boxes and 1 car and the 2 goats. It's very similar. Probably it's different, but let's see what it involves. So number 1, the host picks 3 winning numbers and keeps them secret. Remember, this is the 3 numbers out of 6 lucky numbers game, okay? So the host knows which are the 3 winning numbers. Now, you choose 3 numbers from 1, 2, 3, 4, 5, or 6, and you show them to the host. He knows, well, like he knew which door you'd chosen, he knows which numbers you've chosen, okay? Now then, the host then chooses one of the 3 numbers that you didn't choose and declares that to be a losing number. Now, this is like him opening the door in the car goat problem. Here, he's just saying he knows what numbers you've chosen, so he won't use one of those. He'll use one of the other 3, and he'll say, now this number's not a winning number. And so you now only have 5 numbers in the game. You haven't got 6 numbers anymore. Just like you were reduced from 3 boxes, which you were uncertain about, to 2 in the classic Monty Hall, here you're reduced from 6 numbers to 5. And you have the option to change your choice of numbers if you want to. And again, the question is, should you change your choice? Okay, so that's what we're going to talk about now. And you can see, I think, the similarities with the Monty Hall game, and that it's going to be a little bit more complicated. What do you think, Caroline?
Well, my brain is steaming. I'm I'm thinking, okay, I'm going to learn from Monty Hall, just change, but I'd like to see the numbers.
But Caroline, have you got it in your head how this game works?
Let me review it. So the host, okay, so the host has chosen 3 winning numbers out of 6.
Yes, just like
we've got just based on what we saw before, that's 1 in 20.
Yes.
Okay,
yes.
So that's 1 in 20 based on what we saw before. So, and then I choose 3 numbers from 1 to 6 and show them to the host. Now, it could be that the 3 numbers I picked are the 3 numbers that the host picked. It's possible. Now, out of the remaining 3 numbers that I didn't choose, the host removes one of the numbers. Just one of the numbers between 1 and 6, one of the balls, let's say. Is that correct?
Yes, like he opens a door, so you've only got 2 doors to think about now.
So he might have taken the number 2 out because he knows the number 2 is not in the winning combination.
Exactly.
I'm liking my chances. I'm thinking I've got better chances now. But should I change? Okay, I've gotten the option to change. Okay, so now it's out of 5 instead of out of 6. And I know that the 3 numbers that I've got is now out of 5 because one of the numbers I haven't chosen has been removed.
Well, let's think about this. We need to review the fact that the 3 numbers chosen from 6 are 20 options, and there's the list. And as you said, Caroline, one of these triples of numbers, I've written pairs there, but it's a triple of numbers, must be the winning combination. So there's a 1 in 20 chance of winning. So we know that. That's what you said, Caroline. Now, 1 in 20 is 5%. So that was the standard lucky numbers game, and the Monty Hall version we've just talked about. Let's see how that works. Now,
it's based on that, the 3 numbers I've chosen originally have a 1 in 20 chance of being the winning numbers.
They do, and the chance
if I don't change, my chances are 1 in 20.
Yes,
oh, chance of losing is 19 out of 20. That sounds terrible.
Yes. So now, because we don't know which of this 1, 2, 3, 4, 5, or 6 is removed, instead of listing it with numbers, I've listed these 5 numbers A, B, C, D, E, because it's 5 numbers and it doesn't matter what you call them. Okay. So there are 10 combinations. Can you see that in the top row there, all the combinations that include A are listed?
Yeah.
A, B, C,
there are
A, B,
6
D.
combinations that include A.
Now, there are some more that don't include A. And so below in the middle row, there's the combinations that include B, but not A. So it's B, C, D, B, C, E, and B, D, E. And then the bottom one hasn't got an A in it, hasn't got a B in it, and there's only one possibility.
So by removing just one number, one digit, one ball, there you've now got 1 in 10 possibilities. Had this been the point of choice, instead of 1 in 20, we've now got 1 in 10.
Now, so you've got some more information now. You're told that one of the other numbers, well, not one you've chosen, but one of the other numbers is a loser and it's removed from the game. So now there are only 5 numbers in play, and we've seen that, as you just said, that there are 10 combinations remaining. Now, the chance the chance of one choice of 3 numbers chosen from 5 being the winning combination is now 1 in 10. So it's a lot better chance. And it's very similar to the Monty Hall problem, which we've just considered, that the chance was 1/3, 2/3. Okay, so
Right.
so now, but in the Monty Hall case, in the 2/3 situation, it was certain which door the car was behind, so you knew which one to choose then. Now this is different. We still don't know which triple of numbers we need, but let's see what's happened. By changing one of your 3 numbers, the chance now in 19 out of 20 cases is now 1/10. So that is 19 over, when you work that probability out, it's 19 over 20 times 1 over 10. And that's 9.5%.
So that would be the other route. So if I stick, then I've got 1 in 20 chance of winning 5%.
5%.
And if I change 5%, 1 in 20 chance of winning 5%, I don't know what I said. And if I change, I've now got 9.5%. I've doubled my chances of winning. Almost.
Not
okay,
quite doubled, but almost, yeah.
Close enough for my
Yeah,
liking.
Yeah.
Oh my goodness.
So I think this is a really nice thing to be thinking about, because you've got to really understand the subtleties of probability to understand this. And congratulations, everybody who understands it. And because it isn't.
Now wait, I might have to watch this again and again a few times to understand it.
But it isn't altogether straightforward. But actually, it's clever. And when this was added as a comment to my posting on Facebook, it made me think, and I thought, oh well, that's a nice question. That's made me think very hard.
I think I want an aspirin.
Yes. So, to bet or not to bet, here's a summary of what we've been talking about. So, in recent years, there's been a lot of the sorts of games that you could play in a casino or one of these halls where they have these on bandits. You've got card games, dice games, roulette games.
You can play poker online. You can do all kinds of things online.
So many different things, and that has hooked people, because it's a little bit addictive. I'm not saying it's necessarily seriously addictive for everybody, but it's quite good fun, and you want to win. It's just like all the computer games that kids get interested in, love to play, but I think they're pretty horrible.
You're playing with real money.
You are, but the games that kids play, I think, are really horrible, because they're often shooting somebody, killing people, aren't they?
Yeah, there's other games that cost money that aren't. Well, I mean, but the thing is, they're not gambling games. They're not spend money on them. You spend money on costumes, on characters, on avatars, on armor, different things. But it's not gambling. It is purely spending.
No,
that's a different kind of spend. Being a spendthrift is a different kind of.
They're run for a commercial reason, aren't they?
Yes. This casino online the online casinos are the culmination of the research that those mathematicians did all those centuries ago, though.
Absolutely. So what you see next to it is the very simple game that you can play with 5-year-olds. You can make your spinner with a paper clip and a drawing pin and spin it, and they will intuitively realize, having played it a little bit, even if they're very young, that they've got a 1 in 4 chance of winning. Out of 4 spins, on average, they're going to win once if they stick to the same number. So what we're saying here is that it's an innocent little game, but it is laying the foundations for younger children to understand probability. Now, there you see below that listed all the combinations of 2 numbers chosen from 6, and beside it, the tree diagram, and it's too small for you to see on the screen, but it's got written on the probabilities of each branch, what that branch means. And it was if you want to go back to the recording from last week, we did that in detail. Now, then this lucky numbers game, which we've mentioned several times this evening, which is about the 3 balls out of 6. You need a spinner there with 6 numbers, or 6 cards, or 6 balls in a wheel or a hat, and you pick out 3, and it's 3 out of 6 that give you the winning combination. And there you see listed all the combinations, and there are 20 of them, of 3 numbers chosen from 6. Oh, I should have changed that. It's not 1 in 14 million million. It's 1 in 14 million. That is wrong. Wrong. I wrote it wrong, and I should have changed that slide.
Tony, you made a mistake, and your brain grew.
Yes, that's true. That's true.
But that is a good point. We do have, that is what we said on the recording last week, so that has to be changed.
So there we go. And
oh, look at that. As you watch, ladies and gentlemen.
As you watch.
With us live. The transformation.
There you go.
Correction.
That is 10 to the power 6. Now you could have
changed you could have changed the pairs into triples as well. You could have edited that slide at the same time.
Okay. Yay! Now then, what we've revealed now, with an extra click of my tap of my finger, is the symbol for the National Lottery looks a very friendly face made with somebody's hands, doesn't it? That's the UK National Lottery sign at the back. And up on the right,
yeah, luck. Wish me luck. If I'm lucky.
Yes.
Was it?
Fingers crossed. And up on the right, you have got the Monty Hall diagram that helped to explain how it all worked out with Monty Hall.
So really, the skill of that game was Monty Hall's skill in persuading people to choose the door that didn't have the car behind it.
Yes, yes.
It was.
Yeah.
He must have been good at the psycho. Maybe he was a magician and was really good at getting people.
Well,
to force a choice.
I think he would sow a seed of doubt in the person's mind if they had actually 1/3 of the time chosen the door with the car behind it, and he would be quite genuinely. Sorry, if they'd chosen the door with a goat behind it, he'd try and sort of, sow a seed of doubt, and it might be the right one, there might be a car there, so that they'd stick with their choice of a goat. And in the other circumstance where they had a car, he'd be working very hard, chosen the car, he'd be working quite hard to persuade them to switch, I think.
Yeah, it'd be, are you sure? Is that your final answer? Are you sure?
Yeah. So what else have we got here? So this is in the Monty Hall version of the Lucky Numbers game, which we have those 10 options, and there's the list of the 10 cases. By changing a choice of 3 numbers, your chance of winning goes up from 5% to 9.5%. And so now you've got a summary of most of the things. And now what you see is the word addiction has come up there in both in the halls where you have these machines, and also with online gambling. And then there's a picture of horse racing as well there. And we had a lot of other pictures of gambling situations as well. And the casino could be a live place like Las Vegas. Apparently, in the United States, do you know where a lot of the casinos are in the United States, Caroline?
On Indian reservations.
Yes, indeed. And you see what the invaders did in America was defeat the people who lived there and push them away from the good lands and into the worse lands that were, which weren't very fertile. And
some of them are actually called Badlands.
and but then the legislation in the country was such that there was restrictions on gambling, but those restrictions didn't apply to the Indian reservations. So the Indians, the Native Americans, I should call them.
Yeah, Native Americans. Probably not called the Native American reservations. Apologies.
I shouldn't have called them that. Yes,
me either. I said it. I was the one who started it. I apologize.
Well, okay, so they have been getting rich, and what a good thing, by setting up casinos, and so people have traveled from into their reservation to come to the casino, and yes, it's been very successful for them. So it's really rather a good thing, I think. Yeah.
Well, I hope it is shared by the whole tribe and not creamed off by the rich few.
I don't think they've got that. I don't think they're into the sort of greedy capitalism like necessarily like the rest of us. Okay, so here are some links. There's from the Aiming High. There are those two learning packs with worksheets and notes for teachers if you want to use them in your classroom. It's quite a good thing for young people to discuss the sort of things that we've been discussing, isn't it, Caroline?
Yes,
to be aware
on so many levels. Yes. It's gambling awareness, also awareness of just how slim the chances, and what we discussed last time was how the odds are tipped against you because the owners, the gambling establishments are always going to win. They're the winners. They will always turn a profit.
On average, they make a profit, and they make a fairly comfortable profit, I would say. And indeed, they're the people who are getting rich.
Yeah.
And they're not taking any risks, because the definition of gambling is that if you are a gambler, then you're taking a risk. And in order to get a reward that's bigger than your stake. And of course, that doesn't apply to the bookmakers. It doesn't apply to the bookmakers on the race course, or the people who sell you lottery tickets, or the people who run the casinos. They know that they're going to win. They know.
It's built in.
Yeah, it's built in. And how is it built in? How is it built in? Through mathematical calculations.
Based on the maths that those ancient mathematicians did all those centuries ago.
Well, I think people had some instinctive ideas about the odds before it was formalized into the theory of probability. Yes. So I think it's time to say goodbye from Caroline and me. This has been our Happy Maths Hour. We hope you've enjoyed it. So goodbye for now.
Goodbye. See you next time. Thank you.